Hi, Assalamualaikum and a very good morning. So today we're going to do some tutorial discussion for chapter 4, focusing on the subtopic of 4.1, the Lewis structure. We're going to do tutorial question 3, 5, 7, 8, and 9 together with question 10 respectively. So without any further ado, let us start. So for tutorial question 3, for each of the following element, we need to write the electronic configuration for its most stable ion, and then we need to state the type of the stability. So for question A, we have 13 aluminium. So 13 proton of aluminium equal to 13 electron. So it means that we're going to have the configuration of 1s2, 2s2, 2p6, 3s2, and then 3p1. Okay, and in order for the aluminium to be octet, we need to remove 3 electron, 1 from here and then 2 from here. So it's going to become 1s2, 2s2, 2p6, and hence it's going to have 8 valence electron in the outermost shell, which is n equal to 2, and this going to be an octet electronic configuration. So once we do that, we're going to write the configuration of aluminum 3 plus to be 1s2, 2s2, 2p6 as shown here, and then this will have a noble gas configuration. Next, for question C, we have 26 ferrum. So first, we need to write the electronic configuration. So we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we're going to have 3p6. So in order to make a more stable configuration, what we're going to do is we need to remove 2 electron from the 4s orbital, so minus, because we're going to donate, right? So we're going to donate 2 electron from here, and then 1 electron from the 3d orbital, so that it's going to become 3d5. So as a result, you're going to get 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. So since we are removing 2 electron from here and then 1 electron from here, so it means that we're going to carry a charge of positive 3. And this is a stability of the half-filled orbital. Alright, so we're going to put it as a half-filled orbital configuration. Next, we're going to have the 16 sulfur. So for the 16 sulfur, as usual, we're going to write the electronic configuration in which it's going to be 1s2, 2s2, 2p6, 3s2, and then a 3p4. And from here, the valence electron going to be 6 valence electron because it have 2 plus 4, which is 6, at the highest principal quantum number, which is 6 valence electron at the outermost shell. And in order to become octet, it need to get to 8 valence electronic configuration, which is an octet electron arrangement. And for that to happen, the sulfur need to receive 2 electron. Dia kena tambahkan 2 electron. Okay, as a result, it's going to become S2 minus, and then from 3p4, it's going to become 3p6 here. And the type of stability that it's going to adopt is the noble gas configuration. Alright, and now for question F, we have the 30 zinc. So as usual, we need to write the electronic configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then a 3d10. So here what you can see is that we have a completely filled orbital. And in order to get a completely filled orbital, we need to remove the 2 electron from here. So we're going to remove here, and as a result, it's going to become zinc 2 plus. So it's going to become zinc 2 plus, 2 electron is being removed, and lastly, we're going to get 3d10 here. And this refers to a pseudo-noble configuration or a completely filled orbital. Alright. So for tutorial question 5, using sodium and chlorine as example, we need to explain the difference between an ionic bond as well as a covalent bond. So as what you know that an ionic bond will involve a metal with a non-metal. So our sodium here will become the metal and our chlorine here will become the non-metal. So for an ionic bond to be formed, one electron from the sodium going to be transferred to chlorine. So the first thing that we need to do is to draw the Lewis dot symbol for sodium and chlorine. So for sodium, it's going to have one valence electron. So the Lewis dot symbol is going to be something like this. Meanwhile, for chlorine, it has 7 valence electrons at the outermost shell. And as a result, we're going to draw it to be 1, 2, 3, 4. And then we're going to pair them together, 5, 6, and 7. So the Lewis dot symbol is going to be looking something like this. And then, since we are forming an ionic bond, so one of the electrons from the sodium going to be transferred into the chlorine. And as a result, the electron going to be transferred to the chlorine atom to become chloride ion. So it's going to become an anion with a negative charge. And sodium is going to carry a positively charged ion. So the positively charged and the negative charged ion will create an electrostatic forces, and this represents an ionic bond. Meanwhile, for a covalent bond, it is formed when the two chlorine atoms share the electron together in order to form a chlorine molecule. So as usual, you need to draw the Lewis dot symbol for the chlorine atom. So you have two of them together, and then you can imagine it to be like this, where one electron from one atom sharing electron from another chlorine atom. Okay, so they are need to be close by together, and this region of sharing here will be created, and this is denoted by a single bond because two electrons here representing a single covalent bond. And this is how a covalent bond can be formed through a sharing of electron from each chlorine atom. Now for question B, we need to use the Lewis symbol to show the sharing of electrons between hydrogen and fluorine atoms. So we need to label the electron pairs as bonding pairs as well as the lone pairs. So the first thing first, we need to draw the Lewis dot symbol. So we have our hydrogen, which is H dot here. So hydrogen have one valence electron, so we could just gonna draw it one time. And then when we have the fluorine, so for fluorine, it have 7 valence electron. So it's going to be fluorine, then 1, 2, 3, 4, 5, 6, and 7. So hydrogen here is non-metal, fluorine here is non-metal. So what they're going to do is they're going to share the electron together. So the sharing of electron from hydrogen with the fluorine going to form a single covalent bond. And this single covalent bond here refers to a bonding pair because it refers to a single one. Meanwhile, the pair of electron here will refer to the lone pairs, in which we have 3 lone pairs altogether. And this is how you answer question tutorial 5. Now for question 7, we need to draw the Lewis structure for each of the following molecule, and then we need to state the unusual features, for example, the exceptional octet to the structures. So for the structure number 1, we have the ClF3. So for ClF3, we know that the first thing first that we need to do is to calculate the total number of valence electron. So for Cl, we have 7 electrons, 7 valence electron. And then for fluorine, it's going to be 3 times 7. So you're going to get a 21. So the total number of electrons that we're going to get is 28 electrons. So in between chlorine and fluorine, the chlorine is more electropositive. So since chlorine is more electropositive, and hence it's going to become the central atom. So chlorine going to be attached with 3 fluorine atoms. So it's going to be 1, 2, and 3. 3 fluorine. So we have used up one single bond representing 2 electrons, right? So 2, 4, and 6. So minus 6 electrons. So we're going to left with 22 electrons. This 22 electron is then used up to complete the octet at the terminal atom first. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we have used up 18 electrons. And then we have left with 4 electrons. These 4 electrons here will then use to fill the central atom. So we have 1 and 2, and then we have 1 and 2 here. Alright, so we have a structure of ClF3 now. So as what you can see here, the central atom, which is the chlorine, will have 2, 4, 6, 8, 10 electron. So you're going to have 10 electron, 10 electron dekat central atom. Dan 10 elektron ini adalah lebih besar daripada 8. And because of that, they are known as the expanded octet. Alright, and these structure here are essentially stable. And that is why the exceptional that they're going to adopt is the expanded octet. Okay, now we're going to look into SeF4. So for selenium, the same thing, you need to count the total number of valence electron. So selenium will have 6 electrons because it is located in group 16. For fluorine is going to be 4 times 7, which is 28 electrons. So 6 plus 28 is going to be 34 electrons. So between selenium and fluorine, the selenium is going to be the more positive, a more electropositive atom. So selenium going to be at the center, connecting with 4 fluorine atoms at the terminal. So we have used up 8 electrons in order to make the bonding pairs. So 34 minus 8 going to become 26 electron. And then the 26 electron is used up to complete the octet at the terminal atom. So 1, 2, 3, 4, 5, 6. So we're going to have 12, 18, and then 24 electron. So minus 24 electron. So the balance that we're going to get is 2 electron. The 2 electron is used up to fill in the center here. So as a result, the central atom going to have 2, 4, 6, 8, and 10 electron. So you're going to have 10 electron at the center. So as a result, you're going to form an expanded octet because it is greater than 8 electron. Alright. Now we're going to do NO here. So as usual, we need to find the total number of the valence electron. So the total number of valence electron for NO going to be nitrogen going to be 5, oxygen going to be 6. So the total number of electrons that we have is 11 electron. So N dengan O. So we're going to form a bond in between NO. So minus 2 electron. So in terms of electronegativity, 11 minus 2 going to be 9 electron. So in terms of electronegativity, oxygen is more electronegative. So this one going to be the central, this one going to be the terminal. So we're going to complete the octet at the oxygen first because it is at the terminal. So 9 electron, right? So we're going to be 1, 2, 3, 4, 5, 6. Minus 6 electron. So we have left with 3 electron here. So the 3 electron here will be used up to complete the octet here. Okay, so minus 3 and then left with 0. Okay, so from here, you can see that this is not the most plausible structure because when you calculate the formal charge, the nitrogen will have 5 valence electron, right? Minus 1, 2, 3 lone pairs electron minus 1 lone pair. So it's going to be plus 1. Okay, and the formal charge of this one is nitrogen, this one is oxygen. So formal charge of oxygen, the valence electron is 6, right? Minus lone pair electron. So you count it one by one. 1, 2, 3, 4, 5, 6 minus 1 bonding pair. So you're going to have a structure of minus 1. So positive 1 and negative 1, which is not plausible. So what it's going to do is this lone pair going to be transferred to here. Doesn't matter, you can choose any lone pairs. So once you bring the lone pair to there, what you're going to produce is to be something like this. Okay, so the formal charge can be counted by valence electron minus lone pair electron minus bonding pair. Okay, so when you count the formal charge for the nitrogen, you're going to get 5 minus lone pair electron 1, 2, 3 minus bonding pair minus 2. So you're going to get 0. Formal charge of oxygen 6 lone pair electron, 6 valence electron, sorry, minus 1, 2, 3, 4 lone pairs electron minus 1 and 2 bonding pair. So 0. So they have a charge of 0 here, 0 here, and then also 0 here. So this structure is the most plausible structure instead of this one. Okay, so we're going to draw it to be something like this. So it must have a double bond. Okay, and from here you can see that the nitrogen atom gonna have 2, 4, 6, and 7 valence electron, 7 electron at the central atom. So 7 electron is basically odd, nombor yang ganjil. Tetapi dia adalah stabil kerana dia ada kosong formal charge at both the atoms. And as a result, it's going to have the odd number electron stability. Okay. Now we're going to look into the next question, which is the AlBr3. So for AlBr3, the same thing, we need to count the total number of valence electron first. So aluminium got 3, 3Br going to be 3 times 7, 21, and the total number going to be 24. So between Al and Br, Al is going to be more electropositive. So Al, and then it's going to attach with 3 bromine. Okay, so minus 6, we have 18 electron. So 18 electron will be used in order to complete the octet at the terminal atom. So 6, 12, 18. So all of the electron has been used up and then equal to 0. Okay, and as a result here, the aluminium, so if you were to count the formal charge, you will get 0 here, 0 here, 0 here, and 0 here. So you can prove that to yourself. And then for aluminium here, you can get 2, 4, 6 electron at the central atom. Okay, and 6 electron is essentially lesser than 8, but they are stable. So you know that it is a incomplete octet features, so that they are still existing, but the central atom has less than 8 electron. Okay, so this is how you do question 7. Now for tutorial question 8, we have to draw the Lewis structure of POCl3 and determine the formal charge of each atom in POCl3. So, as usual, we need to count the total number of valence electron first in the POCl3 molecule. So phosphorus will have 5 valence electron, oxygen 6 electron, and then 3Cl going to be 3 times 7, which is 21, and then the total number of electrons that we're going to get is 32 electron. So the phosphorus here going to become the central atom because it is the more electropositive atom. So phosphorus, and then it is bonded with O and 3Cl. So 1, 2, 3, and 4. O here, and then we have Cl, Cl, and then Cl here. So we have 4 bonding pairs, which is 8 electron. So we have valence 24 electron. So this 24 electron is then being used in order to complete the octet at the terminal atom. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So all the electrons have been used up here. Okay, and as what you can see here, this is not yet the most plausible structure, because if you were to count the formal charge of the phosphorus, so formal charge valence electron, which is 5, minus lone pair electron, dia tiada kan, jadi kosong, minus bonding pair 1, 2, 3, 4, minus 1. So you're going to have a charge of plus 1 here. Meanwhile, the formal charge of the oxygen here, formal charge of phosphorus just now, formal charge of oxygen, you have 6 valence electron of the oxygen minus 1, 2, 3, 4, 5, 6 lone pair electron minus 1 bonding pair minus 1. So you will have a charge of minus 1. And then for Cl, this Cl, this Cl, and this Cl is the same, is identical, so you can just calculate it one time. So chlorine will have 7 valence electron minus 1, 2, 3, 4, 5, 6 lone pair electron minus 1 bonding pair. So you're going to have 0 formal charge here. Okay, so you're going to have 0, plus 1, and minus 1. Okay, and 0, 0, 0. So this is not the most plausible structure yet, because what you can do is you can bring the lone pair here into here in order to make a double bond, because phosphorus can form expanded octet. Okay, so you can take any lone pair from the oxygen in order to make it double bond. We doesn't touch the lone pair here because this structure here is already stable. The formal charge is 0, 0, and 0. But this one is negative 1 and plus 1. So we need to try to reduce down the formal charge here. So once we do that, we're going to get the structure to be PO, Cl, Cl, and Cl here. So 1, 2, 3, 4, 5, 6. So you just copy back again. And the formal charge of chlorine is the same as before. So you're going to get 7 minus 6 minus 1, which is 0. So formal charge here is 0, formal charge here is 0, formal charge here is 0. And then the formal charge of the phosphorus, here, you will know that it will have 5 valence electron, minus 0 lone pair electron, minus 1, 2, kena kira satu-satu, 1, 2, 3, 4, 5. 5 bonding pairs, so you're going to get 0 formal charge here. And then for the formal charge of the oxygen, you're going to get, because 2 electron has been used to make double bond, and then you're going to have left with 2 lone pairs. Okay, so formal charge of oxygen, you have 6 valence electron, minus 1, 2, 3, 4 lone pair electron, minus 1 and 2 bonding pair. So it's going to become 0 here. Okay, so 0, 0, 0, 0, 0. So this is the most stable structure, and then it's going to form an expanded octet. Okay, and this is how we draw the Lewis structure of POCl3, which it has a double bond, and we have also write the formal charge of all the atoms that are present in each POCl3. Now we're going to move on to the tutorial question 9, where for tutorial question 9, we need to draw the resonance structure of NO3- as well as the SO3. So as usual, we need to draw the Lewis structure first. So for the nitrogen, it has 5 valence electron, 3 oxygens, it means that 3 times 6, which is 18, minus 1, it means that we receive 1 electron, so it's going to be plus 1. So the total number of electrons that we're going to have is 24 electrons. And then between nitrogen and oxygen, the nitrogen is the more electropositive atom, and then it is bonded with 3 oxygen. Okay, so it's going to become minus 6 electron. Valence, you're going to have 18 electron. Okay, so the 18 electron is used in order to make the octet. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we have used up 18 electron. Okay, and as what you can see here, the nitrogen is not octet yet. Okay, belum octet lagi sebab dia hanya menerima 6 elektron. So what you're going to do is you're going to bring the 2 electron, tak kisah dari oksigen yang mana, in order to make a double bond on this side, or on this side. Doesn't matter. Salah satu pun tak apa. Alright, so what you're going to do, let's say if I'm choosing this position here, and then I'm bringing it to here, what I'm going to get is, then, and this one, because I already transferred 2 electron here, so it's going to become a double bond, and then it's going to left me with 2 lone pairs. Mula-mula ada 3 lone pair, tapi lepas dah jadi double bond, it's going to become 2 lone pairs. Okay, so you can choose any of the lone pairs sebenarnya. Okay, and as what you can see here, it's going to have a negative charge, right? So this whole thing need to be bracket with -1. Alright, and this can be proven if you were to calculate the formal charge. Okay, so if you were to draw the formal charge, if you were to calculate the formal charge at oxygen here, let's say I name it as oxygen A. Okay, so formal charge of oxygen A going to be 6 valence electron minus 1, 2, 3, 4 lone pair electron minus 1 and 2 bonding pair, so I'm going to get 0 here. So formal charge of oxygen B going to become, let's say this one is oxygen B, and here is identical, so you just calculate it one time. 6 valence electron of oxygen minus 1, 2, 3, 4, 5, 6 lone pair electron minus 1 bonding pair. So I'm going to get minus 1 here. And then for the formal charge of nitrogen, I'm going to get 5 valence electron minus 0 lone pair minus 1, 2, 3, 4 bonding pairs. So I'm going to get it as plus 1. So I'm going to get the charge here is 0, here is plus 1, here is minus 1, and then here is minus 1. Okay, so the summation of formal charge going to be 0 minus 1 plus 1 minus 1. 0 plus minus 1 plus positive 1 plus minus 1. So the overall charge that I'm going to get is negative 1. So that is why my summation of formal charge is equal to the charge of the polyatomic ion. Okay, just to show you that on how we can get the charge here, and this is consistent with our drawing. Okay, but the question asks for the resonance structure. So bila resonance, it needs to show that there are more than one or two or more correct Lewis structure. So macam saya cerita tadi, you can take this lone pair to put here, or you can also take this lone pair and put here. This one is step A, or you can use step B, or you can use step C. Salah satu daripada cara berikut, jawapan dia pasti akan sama. And as a result, you can form a double bond here, or double bond here. So for your Lewis structure, for your resonance structure, you're going to get it to be something like this. Okay. So kalau tengok di sini ada double bond at this part, or double bond at this part, or double bond at this part. So what you are draw here is correct. You just need to draw it for 3 possible structures. Okay. And ensure that you use double-headed arrow to show the resonance. Alright. Now we have the SO3. So similarly for SO3, you need to count the total number of valence electron first. So sulfur you have 6, 3 oxygens, which means that 3 times 6, 18. So the total number of electron you're going to get is 24 electron. So between sulfur and oxygen, sulfur going to be the central atom, and it is bonded with 3 oxygen, so minus 6. 18 electron is used up to complete their octet at the terminal. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I'm going to get 18 electron. So 0. Okay. And from here, basically you're going to get the structure at sulfur here, the electron at here is not yet octet. Dia tak cukup 8. Jadi what we're going to do is we can bring 1 electron to here, the lone pair, in order to make a, the lone pair can be used to make a double bond in order to make it octet. Okay, so from here, you can decide to bring it to here. So it's gonna become, okay, to become something like this, or you can choose any of the position. So you can also pick, okay, ini step A, ataupun kamu nak buat step B. Kamu nak buat lone pair dari sini untuk menjadi double bond. So this is also acceptable. Or you can also use the C way. You want to make a double bond on this side here. Okay, so both of these is the correct structure when the sulfur have 8 electron at the center. Okay, tetapi kalau kamu nak buat semua double bond pun begini, can also be accepted because sulfur can make expanded octet. Okay, dia boleh expand dia punya octet menjadi 12 electron at the center. So if you want to draw it like this without any resonance is also okay. Or if you want to draw it to be a resonance structure which consists of 8 electrons at the center, then it is also okay. Alright. So this is how you answer question number 9. So for tutorial question 10, two resonance structures of NCO- are as follows. So we have to determine the formal charge of each atom in both structure P and structure Q. Okay, so we need to calculate the formal charge. And as mentioned, the formal charge can be calculated by finding the valence electron of each atom minus lone pair electron minus the bonding pair. So this is something that you should know. So now we need to find the formal charge for the nitrogen. So for the formal charge of the nitrogen in P, we know that we have 5 valence electron for the nitrogen minus 1, 2, 3, 4 lone pair electron minus 1 and 2 bonding pair. So we're going to get the value of formal charge of N going to be minus 1. So it's going to be minus 1 here. Formal charge of carbon. So for carbon, we're going to have 4 valence electron minus 0 lone pair electron. Tiada lone pair kan? Jadi, we have 4 bonding pair. 1, 2, 3, 4. So we're going to have a charge of 0. And then for the formal charge of oxygen, we have 6 valence electron minus 1, 2, 3, 4 valence elect 4 lone pair electron. And then we're gonna minus 1 and 2 bonding pair. So we're gonna have a charge of 0. So negative 1, 0 and 0 here. So the summation of the formal charge gonna be negative 1 plus 0 plus 0 gonna be minus 1, which is the same as the structure as the charge of the polyatomic ion. And now for structure Q, the similar thing, we need to calculate the formal charge of the nitrogen, carbon, and oxygen. The difference between both of them is the double bond as well as the triple bond here. So it have two double bond, triple bond, and one single bond. So we need to find the formal charge first in order to determine which of the following is the most plausible. So for the nitrogen, we have 5 valence electron minus 1, 2 lone pair electron minus 1, 2, 3 bonding pair. So we're going to get 0 here. For the carbon, we have 4 valence electron minus 0 lone pair electron minus 1, 2, 3, 4 bonding pair. So we're going to get 0 here. And then for oxygen, we're going to have 6 valence electron minus 1, 2, 3, 4, 5, 6 lone pair electron minus 1 bonding pair. So you're going to have -1 at the oxygen here. So carbon is 0, nitrogen is 0. So for the summation of formal charge, it's still -1, which is the same as the polyatomic ion. So both of the structure here is correct and they are resonant to one another. But one of these is more plausible, lagi senang untuk terbentuk ataupun lebih stabil untuk dibentuk. Dan kita tengok pada posisi di mana negative charge itu berada. So in structure P, the negative charge is being carried by the nitrogen. Meanwhile, in structure Q, the negative charge is being carried by the oxygen. So, which of the following structure, for question B, determine the most plausible structure, P ataupun Q? So, sebenarnya, the most plausible structure here will go towards Q. Why is that? This is because between nitrogen and oxygen, so both of them are in period 2, right? So this one is group 15 and this one is group 16. Across a period, the oxygen gonna get more electronegative. So dia adalah more electronegative in comparison to nitrogen. Jadi seharusnya the oxygen will take up the negative charge. And in this case, the oxygen take up the negative charge. But in this case, they are not. So this is why Q is the most plausible structure because oxygen take up the negative charge. So we can say that the most plausible structure is Q. O is more electronegative than N, so oxygen should take up the formal charge of -1 instead of the nitrogen. Okay, so I think that's all for today's video. See you again some other time. Bye!